Okay, so today we're going to be talking about invalidity in monadic predicate logic. And it'll turn out that the actual process that we use to show invalidity in an argument is pretty much the same to what we were doing in propositional logic. But the tricky part here is just to get it into the correct form that we can actually use the same techniques that we were using before. So most of what I'll be talking about in this section is getting it into the correct form. Working out the process once you have it in the correct form is a sort of space-consuming project, and the various steps that we would need to take to do that we've already covered when we talked about the short form the first time. So I'm not going to go into details about that here. If there's a missing link somewhere for you, check out the homework solutions videos, even if you haven't finished doing the homework yet, and you'll see me work out one of these on the board once we've got it into the correct form. But the difficult part is getting it into the correct form, and that's mostly what we'll talk about today. So we've seen how to prove an argument that in monadic predicate logic is valid using a derivation or a proof, pretty similar to what we were doing before. We have a couple of extra rules. But we can't use a proof to show that an argument here is invalid. So we need to show that an argument is invalid by constructing a counterexample. But because we're talking about quantifiers that say, well, something is has X certain property, or all things have a certain property, it can be really difficult to determine whether or not that's actually true because it's talking about all things. So one of the ways that we can sort of make this simpler is we can assume a finite universe or a finite domain that it's talking about. So in the extreme case, we can see if the argument works in a universe that only has one thing in it. Then any statement that says all things are red is really only going to be talking about one thing, because in this universe there's only one thing. So, and I'll talk a little bit more about how to do that. But that's sort of the general strategy here, is to constrain the universe that we're talking about to a finite domain. And if it's possible to find a counterexample in a finite domain, well, then that means that the argument doesn't work. In an infinite domain with more objects, the argument would still have that counterexample. So constructing a counterexample works pretty much the same way it did in propositional logic, but like I said, we have these quantifiers that complicate things. So really all that we're doing here in this chapter is getting rid of the quantifiers. And once we get rid of the quantifiers, then things will work pretty much like they did in propositional logic. So quick refresher on what we did for propositional logic. We were doing using what we're calling the short method here. So this is just a quick reminder on how that works. We have, let's say, this argument where premise 1 is if P then Q, premise 2 is P or S, and the conclusion is if P then S. So the first thing we do is we stick all of these on a line here where we have one slash dividing the different premises, and we have double backslashes for the conclusion. So if we look at this, remember we want to construct a situation with truth values for each of the components here that give us true premises and a false conclusion, because then that's a counterexample. If all the premises are true, then in a deductive argument, the conclusion would have to be true. But if it's possible for the premises to be true and the conclusion to be false, then that's a counterexample. So here we can start with making the conclusion false. We know that there's only one way to make a conditional statement false, and that's if it has a true antecedent and a false consequent. So we can go ahead and do that. So we'll make P true and and S false. That'll give us a false conclusion. That's one of the things we're looking for in a counterexample. Now, because we've made P and S true and false respectively, we have to make P and S true and false throughout the rest of our argument. So we can see now we've got the full truth values that we would need in order to assess the truth value of the disjunction in premise 2. And because one of the two disjuncts is true, which is all we need for a disjunction to be true, that premise is true, so easy enough there. And now we've got a Q over here in our first premise But because q is the only thing left, we can make q whatever value we want. So we'll go ahead and make it true. That'll enable this first premise to be true. So now we have a counterexample where p, q, and s are true, true, and false, respectively. So that's just a quick refresher on the short method stuff. I'll show one example further down the line as well, but these quickly, when we get into larger domains, it becomes kind of impractical to show on a slide in this format. But if you're still confused about how to do the short method, you can go back and look at the old videos, or you can look at the examples that I did for 4.8. So this is how the method for finite universes work. The first thing, we need a little reminder on the short method, but the second thing is, well, what it means for a quantifier statement to be true. So we want to transform the quantifier statement into something else that is easier to work with. So if we think about a universal statement of the form, let's say, for all x's, fx is true, just in case each of its instances, fa, fb, fc, etc., is true. Remember, the lowercase letters here are concrete objects, and f is some property that these objects have. For all x's to have the property f, then it must be true that for every single object, they have the property f. So a universal statement is false just in case at least one of its instances, if a, if b, if c, etc., is false. So if I want to say all, for every object, that object is red, and there's at least one object that is not red, well then the statement that I made about all objects having the property redness is false. Okay, an existential statement is true just in case at least one of its instances is true. If I want to say there's at least one x such that fx, then if I look at fa, fb, fc, etc., until I look at all of the objects in the universe, if at least one of them has the property f, then the existential statement is true, because all I'm saying is that at least one object has this property. An existential statement is false just in case each and every one of its instances, fa, fb, fc, etc., is false. So here we'd have to look at all of the objects in the universe, and if none of them have the property f, then it is not the case that there is at least one object that has the property f. So that should be familiar to you. We've already talked about this. You can see it's much easier to make a universal statement false and an existential statement true than it is to make a universal statement true or an existential statement false, where we have to know something about everything. But to make a universal statement false or an existential statement true, we only need to know a certain thing about one thing. We don't need to know something about everything. Well, we end up knowing something about everything because we know that it's not the case that everything has whatever property of an existential statement is false, or a universal statement is false. But so we can think about universal statements being expressed as conjunctions in this case. So a universal statement is true only if every single object in that universe has that property. So if I say here for all x is fx, then that means that, well, A has property f, and B has property f, and C has property f, etc., until it's a conjunction using all of the possible objects, all of the objects in the universe. All of them at the same time have property f. So existential statements, on the other hand, can be expressed in terms of disjunctions of every object in the domain. So if I want to say there is at least one object that has property f, well, that means that either A has property f, or B has property f, or C has property f. And it's just going to be a disjunction because I only need one of these things to be true. So I have this massive disjunction that has all of the objects in the universe, and if at least one of those has property f, well, then it's true that there is at least one object that has property f. So keeping this in mind, well, my situation got messed up here a little bit. But we can rewrite our quantified formulas into just either existentially quantified formulas we will rewrite as disjunctions, and universally quantified formulas we can rewrite as conjunctions. So if I start with the statement here at the beginning, there is at least one x, gx, and qx. So there is at least one object that has property g and property q. So if I start with just a one object domain, so a one object domain is going to be a universe that has only one object in it. We'll call that object A, just for simplicity's sake. It could be a different lowercase letter that refers to a single concrete thing, but here A is the one object in our entire universe. So in a one object domain, I would rewrite this existentially quantified statement as, well, GA and QA. If it's true that at least one object has property G and has property Q, and here we only have one object in the universe, well then that one property must have, or that one object must have property G and property Q. So I can just rewrite it as GAQA. Looks kind of like instantiating. However, if I want to have a larger domain, let's say a two-object domain, then things get a little bit different. So if I go to a two-object domain, where here we have a universe with two objects in it, and I'll see how to phrase the statement. There is at least one object that has property G and has property Q, and in the universe there's two objects. Well then, I have to make a disjunction. Either it's true that object A has property G and has property Q, or object B has property G and has property Q. So you can see it looks like where the first part of the disjunction looks like it did in a one object domain, but I've added a disjunct to it because we have another object to consider. Either our first object has property G and property Q, or our second object B has property G and property Q. Because there's two objects in this universe, we need to consider two possibilities if it's true that at least one object has property G and property Q. So we could change this existentially quantified formula into this other formula that just has constants in it. So we can do the same thing with universally quantified formula. So we've got a different operator here. We have for all x's, if fx, then qx. In a single object domain, universals get real easy, because if there's only one thing in our universe, well then just to say all things have property whatever is the same thing as saying, well, at least one thing has property f or q in this case. So in our single object domain, we just say, well, if it's true that for all x's, if fx, then qx, well then our one object in this case, if it has property f, then it has property q. So that's true for A, the only object in our universe. Now, if we get to a larger domain where we have two objects, well, think about it. Our original statement is saying for all x's, if x has property f, then x has property q. So we need to have two statements here, where first is our first object, if A has property f, then A has property q. And it's true that if B has property f, then B has property q. So here we're using a conjunction that recasts the initial formula that we were given to show that if for the statement to have the same meaning, where it says for all x's, if fx, then qx, then I need to just specify that I'm giving a conjunction of every single object in this universe having this relationship. So we have two objects, A and B, so I know that it must be true that, well, if A has property f, then A has property q, and it must be true that if B has property f, then B has property q. So this is a basic sketch of how you do, um, you transform a quantified statement into this more concrete version. And once we have this concrete version, then we can actually look for counterexamples to show validity and so on. Invalidity, I mean. Now we can expand this to a 3-object domain, but you can sort of see what the formula is here. It would just keep increasing in terms of adding disjuncts or adding conjuncts, depending on if it's a existentially quantified formula or universally quantified formula. So you might wonder, well, what about formulas without a quantifier as the main operator? In the previous examples here, both our existentially quantified formula and the universally quantified formula had the quantifier as the main operator. But that might not always be the case. So here, for example, we have, well, there is at least one x gx and there is at least one x qx. So here the conjunction is the main operator, not one of the quantifiers. So in a one-object domain, it's real simple. There's only one object, so it must be true that A has property G and A has property Q. Because we're saying there's at least one object that has property G and at least one object that has property Q. And so if we only have one object in our universe, well, then A is going to be the thing that both of those properties inhere in. So that's no problem. But if we have a 2-object domain, then it would look like this. So the conjunction would stay as the main operator here, and we would just change what's inside of the scope of each of the quantified formulas. So we change, well, there's at least one x gx to either A has property G or B has property G, and it's true that either A has property Q or B has property Q. Because our original statement was there is at least one thing that has property G and there is at least one thing that has property Q. And in this 2-object domain, well, there's two objects in this universe. We don't know which one is going to have which property, but we know that at least one of them has each of these properties. So we need to have a disjunction between each of the possibilities here. So similarly, with a universally quantified formula, here we have for all x is gx and for all x is qx. In a single domain, this is real easy. We have all objects in our universe have property G and all objects in our universe have property Q. And I messed up writing this one. So this should be GA and QA. So that's on me. Let me fix that real quick. Okay, fix that. So in a 1-object domain, you'll see that, well, this looks actually the same as our existentially quantified formula, or our pair of existentially quantified formulas earlier. Well, that makes sense, because if there's only one object in our universe, then saying, well, at least one x has property G and at least one x has property Q is the same as saying all x's have property G and all x's have property Q. Because there's only one object, it's going to turn out the same. So we have here, well, A has property G and A has property Q. Now in our 2-object domain, you're going to see that instead of a disjunction, we're going to get a conjunction. Now the major operator is going to stay the conjunction because what we're changing is just what's on either side of the conjunction that we were given in our original statement, which is for all x is gx and for all x is qx. So we're just changing the quantified formulas into something more concrete. So here in our universe that has 2 objects, well, we can transform the statement for all x's gx into, well, A has property G and B has property G. Those are the 2 objects. Those are all of our objects in our universe. So all properties in this universe, or all objects in this universe, have property G. And it's true, our second conjunct here, that for all x's, qx, which means for everything in this universe has property Q. So our second conjunct here, when we transform this, is going to be, well, A has property Q and B has property Q. We're going to, each of our objects in our two object domain are going to have property Q because, like we said in our original statements, everything has property Q. So we're just going to list everything concretely and show that it has that property. Okay, so that's sort of the tricky part, is just transforming those existentially quantified statements into the finite universe domain. And then once we do that, we apply the short method to show invalidity. All right, so the first thing we're going to do is pick a universe of discourse, or a domain. So all that matters here is how many objects are in that domain. So for example, we can have just A as our one object domain. We have AB as our two object domain, ABC as our three object domain, etc., etc. So rewrite the premises and conclusion of the argument as conjunctions or disjunctions. So existential statements become disjunctions of all the objects in the domain, and universal statements become conjunctions of all the objects in the domain. After we've done that, we've transformed the argument in a way that removes all the quantifiers, and then we can just apply the short method to show invalidity. So we'll look at some examples. So we'll start with this argument, and we'll start with in a one object domain. So premise 1 says, for all x's, if fx, then gx. And premise 2 says, well, there is at least one x, hx, and gx. And our conclusion is, for all x's, if fx, then it is not the case that hx. So in one object domain, this is pretty simple, because all x's, for all x's, if fx, then gx, well, we only have one object here, so that means that if our one object has property f, then our one object has property g. And our second premise is there is at least one object that has property h and has property g. So our one object has property h and has property g. Easy enough. And our conclusion is, for all objects, if that object has property f, then it is not the case that it has property h. So if our one object here, A, has property f, then it is not the case that A has property h. So we'll set this up all in one line like we do for the short method, and we can start thinking about what we would need to do in order to have true conclusions and false conclusions and true premises. Or a false conclusion and true premises. So the first thing we can see is that, well, we've got a conditional as our major operator here in the conclusion, which means that we need to have a true antecedent and a false consequent. So because the consequent here, the major operator, is a negation, well, we need HA to be true. That will make the negation of HA false, which will then make the conditional false. So we have a false conclusion with this valuation. So the next thing to do is go ahead and apply that valuation to everywhere else in our argument where FA and HA show up. So we can see we've done that here. Well, and then the next thing to do is, well, we're looking at the value for GA. GA can be anything. We're not really constrained by that. But, well, we see that the major operator of the second premise is a conjunction, which means that in order to make the second premise true, in working towards a counterexample, it has to be the case that GA is true. And that would allow this premise to be true. Otherwise, this premise would be false, and we wouldn't be able to get a counterexample that way. So GA has to be true. So we go ahead and make GA true over here, and it turns out that if FA and GA are both true, then this conditional is true, and we have a counterexample where FA is true, GA is true, and HA is true. So you can see that once you have given the argument in some finite domain, it really just works the same as things did in propositional logic, where we've got two letters here. We have a capital letter and a lowercase letter conjoined, but as far as assigning truth values and stuff, we can just go ahead and look at each of them and try to find false conclusion and true premises the same way we did before. So the tricky part here is just getting it into this structure, and then once you do that, it's the same as what we were doing with propositional logic. Okay, so that's one example, and well, I messed up here and spoil the answer. I'll go ahead and get rid of this real quick. Okay. So hopefully, if you saw the answer before, hopefully you didn't write it down or anything. Because in this example, well, two object domain things end up getting longer. We're not really going to have enough space on the slide to show the whole thing. So I would like you guys to, after we've shown how we transform the argument into a finite universe structure, that you see if you can work it out on your own to find the counterexample, and then I'll list the answer for the counterexample for you. So here we've got our first premise, for all x's, if x, then gx. Our second premise is, well, there is at least one x, hx, and gx. And our conclusion is, for all x's, if fx, then it's not the case that hx. Same thing we did before. We already found a counterexample, but we're using the same one again to show you how to set it up with a two-object domain. Of course, if you're doing one of these on an assignment and you find a counterexample in a single object domain, and the question doesn't ask you to find it in a specific number size domain, then you can go ahead and stop there. You don't need to go and find counterexamples in other domains as well. One counterexample is sufficient to show that any argument is invalid. Okay, so we've got our two object domain, A and B. So the first premise is going to look like this. It says, the way it was originally written, for all x's, if fx, then gx. So for all objects, if an object has property f, then that object has property g. So we've only got two objects in our universe here. So we can say that, well, if A has property f, then A has property g. And if B has property f, then B has property g. And if we had an additional, if it was a three-object domain, then we would have to put parentheses around this to keep it a well-formed formula, and add another conjunction, which says if C has property f, or we had another conjunct that says if C has property f, then C has property g. So we just have as many conjuncts as we have objects in our domain. All right, our second premise is going to be what the original version reads: there is at least one x such that hx and gx. There is at least one object that has property h and has property g. So here, well, we only have two objects in our universe, so we have a disjunction between the two, where either it's true that A has property H and A has property G, or B has property H and B has property G. Maybe they both have both properties, but we know that at least one of them does, because our original premise 2 said there's at least one object that has property H and has property G. So we just list all the possible objects and say, well, it's one or the other of these. It's a disjunction. Okay, so our conclusion is for all x's, if fx, then it is not the case that hx. So again, we're going to get a conjunction because this is a universally quantified statement. It says for all objects in our universe, and so we've got two objects in our universe, so we have two conjuncts. If A has property f, then it is not the case that A has property h. And if B has property f, then it is not the case that B has property h. So this eclipses the totality of objects in our universe here. So it has the same meaning. Okay, so not enough room here to really work through this whole thing. So if you'd like to practice this, go ahead and go and pause the video, try to see if you can find a counterexample now. Just using the short method, write each of these premises out on one line, and see if you can find a way to make this conclusion true, or sorry, this conclusion false, and premises 1 and 2 true at the same time with a consistent valuation. But, so once you're done with that, this is a counterexample. So when FA is true, FB is true, GA is true, GB is true, HA is true, and HB is true, we get a false conclusion and true premises. So that would be how we would list the counterexample. Okay, so what about an argument that has constants in it? So in this case, our first premise is a universally quantified formula. It says, well, for all x's, if fx, then it is true that gx or hx. Our second premise is just fa. Our third premise is it's not the case that hb. And our conclusion is there's at least one x such that fx and gx. Well, we can see because a constant was specified in the argument in the first place, and here we have A is a constant and B is a constant, well, we can't have a single object domain because we're already given two different objects in the argument. So the smallest domain that we can have here is a two-object one, A and B. And A and B are already accounted for in the example, or in the argument. So this isn't actually a problem at all. We just incorporate whatever the constants we were given. We make sure that we use those as part of our domain. And well, we know that there is at least some object A and some object B because our argument refers to those. So let's just say that those are the only objects in our universe and see where we go from there. So we would rewrite the first premise like this. Originally it says for all x's, for every object, if that object has property f, then that object either has property G or property H. So here we have two objects, so we'll just write what that means in each case. So if A has property F, then A has property G or has property H. And it's very important to remember that a universally quantified statements are conjunctions. And it's true that if B has property F, then B has property G or H. Our second premise we just rewrite as is. Our third premise we just rewrite as is. Our conclusion we need to change because it was an existentially quantified formula. So we get our original conclusion read, there was at least one object in this universe that has properties F and has properties G. So here we only have two objects. We have object A and we have object B. So we'll go ahead and write, well, either object A has property F and has property G, or object B has property F and has property G. So we've rewritten our conclusion in that way. So I'll go ahead and, before showing you the answer, if you want to pause and work on this, please do that. It's good practice. But something that will be a bit of a hint here is that, well, FA just has to be true, and HB has to be false for premises 2 and 3 to be true. So we've already been given something pretty concrete to work with. Normally it's easiest to start with finding a way to make our conclusion false and then seeing if we can make our premises true given the restriction that exists with our conclusion being false. But here, we have a couple premises that are just FA. In order for premise 2 to be true, FA has to be true. So we can go ahead and make FA true in every other case. And HB has to be false in order for not HB to be true to make premise 3 true. So we can go ahead and make HB false in all of the instances that it shows up in our arguments. Now that gives us some restrictions to work with that'll make it easier to find a way to, with that valuation, to make the conclusion false, and then to make the first premise true as well. All right, so here's the answer if you finished working on it. So we have a counterexample when FA is true, FB is false, GA is false, GB is false, HA is true, and HB is false. Didn't do any of the work here. I would ask on the test that you actually do the short method and work your way through it and show me the work. It just won't fit on the slides, and in the homework examples, I give some. I work through those, and you can see how to do them there. All right. So this got all messed up. So we're gonna go back and erase that real quick. So if hopefully you didn't pay too much attention to what the conclusion is if you wanted to work on it, but I'll fix that real quick. Okay. This should work better here. So here we have one premise and a conclusion. So we have our premise is, well, object A, if object A is property F, then object A has property G. And our conclusion is, well, there is at least one X such that if X is property F, well, sorry, I was looking at this wrong. So our conclusion says, if there is at least one X that has property F, then there is at least one X that has property G. So we're going to look at this in a two-object domain. So the domain isn't going, whatever domain we're going to have is not going to affect our first premise because we just already had a constant attached to it anyway. So that's going to stay exactly the same. Our first premise is just, well, if A is property F, then A is property G. But because we have two objects in our domain, we're going to need to expand our conclusion a little bit. Now our conclusion says that the main operator of our conclusion is a conditional between two existentially quantified formulas, where the antecedent says there's at least one object that has property F, and our consequent says there is at least one object that has property G. So the new conditional statement that we're going to get for a conclusion here, the antecedent is going to say, well, either A has property F or B has property F, because those are the two possible objects, and we know that at least one object in the universe has property F, so we'll list them out here. Either A has property F or B has property F. Then, either A has property G or B has property G. So again, list out the possibilities of our universe and have them in a disjunction. So take a minute to try to figure this one out. A way to make this conclusion false while the premise is true. And the answer for this one is going to be, well, you get a counterexample when FA is false, GA is false, FB is true, and GB is false. All right, so that's basically how these are done. Something to keep in mind here is if you cannot find a counterexample within a domain of 2 to the n objects, where n is the number of predicate letters, then the argument form is valid. It has no counterexample. So it's not as if we have to keep making domains until infinitely larger or whatever until we find a counterexample. There is a cap at which on a domain of this size, if there's no counterexample, then there just isn't a counterexample. But in most cases, and this should be obvious as the way to solve these, because you can see that things get increasingly complicated and it becomes more and more difficult to make conclusions false and premises true, etc. Not so much difficult, but it takes a lot more time to do that when we add a bunch of disjunctions and conjunctions to make things larger and larger, and every time we increase the size of the domain, we add a conjunction or a disjunction to every single instance of a quantified statement. So the best way to solve these is to start with the smallest possible domain, one object domain, and then work your way up from there. So because in most cases, the argument is going to be invalid with less than the maximum number of objects that you would need in order to be sure that there's no counterexample. So because it's easier to do these with smaller domains, go ahead and start with a single object domain. If you can't find a counterexample in a single object domain, try a 2-object domain, then a 3-object domain, etc. Yeah, and if you get to a point where you get to a domain that's 2 to the n objects, where that's going to be whatever number of predicate letters we have, and there is no counterexample, then um, then it's a valid argument. Okay, so that's going to be the end of these. This is actually the last thing I've recorded for this class. If you've actually sat and watched all the way through this, I don't think that many people have actually watched through these, but if you did, um, on the final exam for the extra credit question, if you're doing this by hand, if you go ahead and draw a turtle, and if you're doing this digitally, if you include a picture of a turtle somehow, you could draw one as well if you like. But if you include a picture of your turtle somewhere next to your extra credit question, you'll get an additional 2 points for free. Just for actually taking the time to watch these. This has been kind of a weird experience to try to record all these lectures, because the content of this class is the kind of thing that once you get it, it's sort of obvious. So it's hard to explain things in such a way that anticipates where questions might arise. And when I've done this before as a TA, we've just been in the classroom. So if we're working through something and someone has a question, they can just stop me right there, and then we can work through what the issue is. But so doing this all on my own in a room or on a light board has been really weird. This is my first time doing one of these online classes. My first time as an instructor of record in general. But anyway, I'm babbling. I appreciate it if you watch these. Hopefully it'll help in a week or so when they ask for student evaluations. I'll send a reminder out about those. But it would be especially helpful for me to get feedback on this, because if I did something terribly, I want to know to be able to fix it in the future. If I did something well, then having that on an evaluation is just instrumentally helpful for me getting a job in the future. So either way, I'd appreciate it. If you hated the class, please tell me why, or what you think I could have done to improve. And like I said, draw a turtle or something. In the extra credit question on the 3rd exam, you'll get 2 extra points on me. All right, that's all for this class, and we're almost done. So 1 more week, and that'll be it.